Superconductors, materials that can conduct electricity without resistance, have long fascinated scientists and engineers alike. Their discovery in the early 20th century marked a turning point in our understanding of matter and paved the way for revolutionary technological advances. The phenomenon of superconductivity, first observed by Dutch physicist Heike Kamerlingh-Onnes in 1911, defies the conventional wisdom of electrical conduction. In ordinary conductors like copper or aluminum, electrons flowing through the material encounter resistance, losing energy as heat. Superconductors, however, allow electric current to flow indefinitely without loss, provided they are kept below a certain critical temperature. This unique property has immense implications, from power transmission to quantum computing, and continues to inspire research into new materials and applications. At its heart, superconductivity is a quantum mechanical phenomenon. When cooled below their critical temperature, superconducting materials undergo a phase transition that fundamentally alters their electronic structure. The electrons within these materials form so-called Cooper pairs, named after physicist Leon Cooper. These pairs behave in a coordinated fashion, moving through the atomic lattice without scattering off impurities or lattice vibrations, which are the usual culprits behind resistance. This collective behavior is described by the Bardeen-Cooper-Schrieffer (BCS) theory, formulated in 1957, which remains one of the crowning achievements of condensed matter physics. The existence of an energy gap in the electronic density of states prevents thermal excitations from breaking the Cooper pairs, ensuring the persistence of the superconducting state. The absence of electrical resistance is not the only remarkable property of superconductors. They also exhibit the Meissner effect, whereby a superconductor will expel magnetic fields from its interior when it transitions into the superconducting state. This perfect diamagnetism is a striking demonstration of the quantum coherence present in the material. The Meissner effect leads to phenomena such as magnetic levitation, where a superconductor can be made to float above a magnet or vice versa, seemingly defying gravity. This property hints at the rich interplay between superconductivity and magnetism, a subject of ongoing research and technological interest. Early superconductors were metals such as mercury, tin, and lead, which required cooling to temperatures near absolute zero using expensive and cumbersome liquid helium. This limitation meant that superconductivity remained largely a laboratory curiosity for decades. The breakthrough came in the 1980s with the discovery of high-temperature superconductors, a class of ceramic materials based on copper oxides, known as cuprates. These materials could become superconducting at temperatures above the boiling point of liquid nitrogen, 77 Kelvin, making cooling much more practical and affordable. The discovery of high-temperature superconductivity by Bednorz and Müller in 1986 earned them the Nobel Prize and ignited a global race to find materials with even higher critical temperatures. High-temperature superconductors opened up a host of new possibilities. Power transmission lines made from superconducting cables could, in principle, deliver electricity over long distances with zero loss, addressing one of the major inefficiencies in modern power grids. Superconducting magnets became essential components in medical imaging, particularly in MRI, magnetic resonance imaging scanners, where their ability to generate strong, stable magnetic fields revolutionized diagnostic medicine. Particle accelerators, such as those used at CERN, rely on superconducting magnets to steer and focus beams of charged particles, enabling experiments that probe the fundamental structure of matter. Despite these successes, the widespread adoption of superconducting technology has faced significant challenges. Most high-temperature superconductors are brittle ceramics, difficult to manufacture into wires or tapes, suitable for large-scale applications. Maintaining the low temperatures required for superconductivity still involves considerable cost and complexity, especially for applications outside specialized environments. Researchers continue to search for so-called room-temperature superconductors, which would operate under ambient conditions and truly revolutionize the electrical infrastructure. In 2020, a team reported evidence of superconductivity at 15 degrees Celsius in a hydrogen sulfide compound under extremely high pressures. But reproducing such conditions outside the laboratory remains a formidable obstacle. The quest for new superconducting materials is driven by both experimental exploration and theoretical insight. Advances in computational materials. Science have enabled researchers to predict the properties of hypothetical compounds before they are synthesized in the lab. The interplay between chemistry, crystallography, and quantum mechanics determines whether a material will exhibit superconductivity and at what temperature. Some of the most promising candidates involve hydrogen-rich materials under pressure, inspired by the idea that metallic hydrogen itself might be a room-temperature superconductor. The synthesis of such materials often requires diamond anvil cells capable of generating pressures millions of times greater than atmospheric, pushing the boundaries of experimental technique. Beyond traditional applications, superconductors are poised to play a central role in emerging technologies. Quantum computing, for example, relies on the manipulation of quantum bits or qubits, which must remain coherent for extended periods to perform meaningful calculations. Superconducting circuits, particularly those based on Josephson junctions, form the backbone of several leading quantum computer architectures. These devices exploit the macroscopic quantum coherence of superconductors to create and manipulate superpositions of quantum states, a feat impossible with classical electronics. The development of scalable, fault-tolerant quantum computers could transform fields as diverse as cryptography, materials science, and artificial intelligence. Another area of intense interest is the use of superconductors in magnetic energy storage and transmission. Superconducting magnetic energy storage, SMES, systems can store large amounts of electrical energy in the magnetic field generated by a persistent current in a superconducting coil. Because there is no resistance, the current can circulate indefinitely, making SMES an attractive option for stabilizing power grids, especially those incorporating intermittent renewable energy sources. Superconducting cables, already deployed in pilot projects around the world, offer the promise of compact, efficient power transmission in urban environments where space and energy losses are at a premium. Transportation is yet another domain where superconductors may have a transformative impact. Maglev, magnetic levitation trains, which float above their tracks using superconducting magnets, can travel at extremely high speeds with minimal friction. Japan's superconducting maglev trains have achieved speeds exceeding 600 kilometers per hour in test runs, demonstrating the potential for rapid, efficient intercity travel. The elimination of mechanical contact between train and track reduces wear and maintenance costs, while the absence of resistance in the superconducting magnets improves energy efficiency. Superconductors also find use in highly sensitive measurement devices. SQUIDs, superconducting quantum interference devices, are among the most sensitive magnetometers available, capable of detecting magnetic fields as weak as a few femtoteslas. These instruments are invaluable in fields ranging from geology to medicine, where they are used in techniques such as magnetoencephalography to map brain activity. The exquisite sensitivity of SQUIDs arises from the quantum mechanical properties of superconducting loops interrupted by Josephson junctions, which allow for the detection of minute changes in magnetic flux. The future of superconductivity is intertwined with advances in materials science, cryogenics, and our understanding of quantum phenomena. One of the most tantalizing prospects is the realization of superconductors that operate at room temperature and ambient pressure. Such materials would render obsolete the need for elaborate cooling systems and unlock a host of new applications, from lossless power grids to ultra-efficient motors and generators. The discovery of such a material would likely trigger a technological revolution on par with the invention of the transistor or the harnessing of electricity itself. Research into unconventional superconductors continues to yield surprises. Iron-based superconductors, discovered in 2008, represent a new family of materials with distinct properties from the cuprates. Their complex phase diagrams, involving intertwined magnetic and superconducting orders, challenge existing theoretical frameworks and offer new avenues for exploration. Organic superconductors, heavy fermion systems, and topological superconductors each bring their own unique characteristics, broadening the landscape of possibilities. Topological superconductors, in particular, are of great interest for their potential to host exotic quasi-particles known as Majorana fermions, which could serve as robust building blocks for quantum computers resistant to decoherence. The study of superconductivity also sheds light on fundamental questions in physics. The interplay between superconductivity and other forms of electronic order, such as magnetism and charge density waves, reveals the richness of collective behavior in quantum materials. The mechanisms underlying high-temperature superconductivity remain a subject of intense debate, with competing theories invoking spin fluctuations, electron-phonon coupling, and other interactions. Understanding these mechanisms may not only lead to better superconductors, but also deepen our grasp of correlated electron systems more broadly. In practical terms, the deployment of superconducting technologies faces both technical and economic hurdles. The fabrication of superconducting wires and tapes with sufficient flexibility, strength, and current carrying capacity is a major engineering challenge. The development of reliable, cost-effective cryogenic systems is equally important, as is the integration of superconducting components into existing infrastructure. Nevertheless, progress continues apace, with incremental improvements in materials processing, cooling technology, and system design gradually expanding the reach of superconductivity. Education and public engagement are also crucial for the advancement of superconducting technology. As with many scientific breakthroughs, the path from laboratory discovery to societal impact is often long and uncertain. Raising awareness of the potential benefits and limitations of superconductors can help foster informed decision-making by policymakers, industry leaders, and the general public. Initiatives to train the next generation of scientists and engineers in the principles and applications of superconductivity will ensure a steady pipeline of talent to drive innovation forward. International collaboration plays a key role in the field of superconductivity. Large-scale projects such as particle accelerators, fusion reactors, and advanced telescopes rely on the expertise and resources of multiple countries. Sharing knowledge, data, and best practices accelerates progress and helps avoid duplication of effort. The global nature of the energy and transportation challenges that superconductors can address underscores the importance of cross-border cooperation in research and development. Environmental considerations are increasingly shaping the direction of superconducting research. The transition to renewable energy sources, such as wind and solar, places new demands on power grids, including the need for efficient energy storage and transmission. Superconducting technologies can help meet these demands, reducing greenhouse gas emissions and supporting the shift to sustainable energy systems. The development of environmentally friendly superconductors, utilizing abundant and non-toxic elements, is an important goal in this context. As we look to the future, the magic of superconductors lies not only in their ability to defy resistance, but also in their capacity to inspire new ways of thinking about matter, energy, and information. The pursuit of ever higher critical temperatures, novel materials, and innovative applications continues to push the boundaries of science and engineering. Each breakthrough brings us closer to a world where the flow of electricity is as effortless as the fall of light, where quantum phenomena are harnessed for computation and communication, and where the limits of technology are set not by nature, but by our imagination. In summary, superconductors represent one of the most intriguing and promising frontiers of modern science. Their unique properties challenge our understanding of the physical world and offer solutions to some of the most pressing technological challenges of our time. From lossless power transmission to quantum computing, from medical imaging to high-speed transport, the applications of superconductivity are as diverse as they are profound. The journey from the first observation of zero resistance in a mercury wire to the ongoing search for room-temperature superconductors is a testament to human curiosity, ingenuity, and perseverance. As research continues and new discoveries emerge, the magic of superconductors will undoubtedly continue to captivate and transform our world.